Today we study gauge invariance of a Schrödinger equation. In the previous class we have derived the Schrödinger equation for a charged particle, and the final result was IH bar C d0 psi equals minus h bar squared divided by 2m d squared psi, where psi is the wave function and d is covariant derivative. Covariant derivative has zeroth component, and the spatial component like that. That is just the sum of usual covariant derivative. There's a gauge covariant derivative and the usual covariant derivative plus IQ over h bar c vector potential. That vector potential is a full vector potential. As we know, covariant derivative has the zeroth component 1 over c time derivative, and the spatial derivative has negative sign in front of it. And A mu is the full vector potential. We remember that A mu is gauge field. The electromagnetic potential has some degree of freedom, right? There are many full vector potentials that can generate the same electromagnetic field. The E field and B field can be the same with different A. That is our problem. Because A dependence explicitly appears in the equation, this equation depends on gauge. But gauge must not appear in the final result for a physical observable, because electric field and magnetic field does not change. They are independent of gauge. So we have to solve some problem that the wave function psi must have some gauge dependence in such a way so that the gauge dependence finally disappear in physical observable. It is a little bit non-trivial, but today we will resolve this problem. Why don't we introduce some gauge transformation from A mu to another A? Let me call it A prime, with the same electric field and magnetic field. Then we have to introduce some transformation of the wave function psi from this gauge to another gauge. If it is independent of that gauge, then it becomes nonsense because this equation itself changes. So the solution of psi may change. It is a complicated coupled equation. So let us just assume matrix U that is multiplied to the wave function psi that has been defined for a gauge A mu, and psi prime is the wave function when we make a gauge transformation from A mu to another A, that is A prime. Then physics law must be covariant and the physics equation must be the same in the form. So I assume that new Schrödinger equation written in another gauge must be in a similar form. The only difference is that they are replaced by prime. D0 and D vector, they have different A, that must be replaced by A prime. In that case, psi has been changed in such a way the physics doesn't change. So we have assumed the covariance of the Schrödinger equation. Okay, so we assume that psi prime is transformed in such a way U is multiplied to the original wave function psi. So substitute this in here. All right. You must guess what I want to do. What I want to do is make some transformation of this equation to reproduce the original equation in the previous gauge. Okay, what should I do? The best choice is multiply some transformation, inverse transformation matrix to the left-hand side, and to see that overall matrix is the same as the original derivative for d0 and d squared. So let me first recall that some measurable, the number of particles. Okay? Even though wave function itself can be transformed into another wave function up to over phase factor, that does not change any probability density, something like that. That is physical observable. So that probability density function must be independent of gauge transformation. So that is the most important assumption. So if we make a transformation, this kind of gauge transformation to this wave function, the result is psi dagger, u dagger u psi. Then must be the same as psi dagger psi. That means u dagger u is identity. This is the fact that u must be unitary. Unitary means u dagger is a u inverse. Aha. So u must be unitary. So why don't we multiply the inverse matrix for u, that is now u dagger, to the left-hand side of this equation. Then what we find is this guy is this. What I want to do is interpret this as d0, original, and this guy is just d squared before the transformation. Then means this d0 prime transformation is d0, and the d vector squared is d squared. A solution can be found if we, for any indices, it's just u dagger d prime mu u is equal to d mu. For example, if I apply, this one is true for the first one, and if we introduce this twice, then u dagger d prime I u dagger d prime I u. Then it becomes the di, becomes the di, so it becomes the d vector squared. Okay, so it is the simplest solution, and it seems plausible. So I'd like to find the transformation u that satisfies this kind of relation. But let us be more specific. The gauge transformation, we have introduced an implicit gauge transformation, but we can introduce an explicit form. For example, if we introduce gauge transformation by adding the 4 vector potential by derivative of an arbitrary scalar function, Lorentz scalar function, and why don't we compute the field strength tensor? You remember field strength tensor is depending on the electric field and magnetic field only. So that is a physical, all components are physical. So that must be independent of gauge. So if we substitute this A prime in here, we substitute to the definition round mu A prime nu subtracted by round nu A prime mu. Then this contribution will generate the original F mu nu, and remaining pieces are 2 terms. And we know the double partial derivative with respect to mu and mu cancel exactly. So we have found that this is a gauge transformation that does not change electric and magnetic field. In that case, we require this relation. U dagger d prime mu u equals d mu. If we substitute d mu is in here. And what is d prime mu? D prime, this is d mu, and d prime mu equals same thing, iq over h bar c, a mu plus around mu chi, right? Because I have replaced a by a prime. So that is written in here to the left hand side, and right hand side d mu is just copied. So around mu, the normal derivative, covariant derivative, plus iq h bar c a mu. Okay. Now, chi is just a Lorentz scalar, just a number. We assume that the chi commutes with u, and let us assume one more piece. A mu commutes the transformation matrix U. It is not general for the SUN case, n is not equal to 1, but it is true in this case that if we consider the electromagnetic interaction, it is just a U1 electromagnetic interaction. So we can assume this. Then this guy passes, except that we have a derivative of U. So when we pass this U to the left hand side, I have remaining this remnant, U dagger and partial derivative of U. And except that, this guy passes everything. And U dagger U is identity. And this is original covariant, gauge covariant derivative plus this new contribution coming from the gauge transformation. If we compare this with the right hand side that has this and this contribution, our equation gives the condition that this partial derivative piece, so U dagger round mu U, and the gauge transformation contribution in here, they must cancel exactly. This one shows that the gauge transformation from A to A prime, that is around mu chi, that is an additional contribution, that can be determined like that. So using this equation, I can determine round mu chi. So gauge transformation must be made in such a way that this chi is not free, but that is determined by the transformation matrix U in this way. A mu minus I h bar c over q U dagger round mu U. So U is the gauge transformation matrix for the particle. It is very important to notice that once a particle acquires electric charge, then it interacts with light. And light has gauge degree of freedom, but that gauge degree of freedom does not contribute to any physical observable. So, and one more thing we have to remember is Schrödinger the equation itself is depending on gauge, but explicitly in this way, the covariant gauge covariant derivative has explicit gauge dependence, but any physical observable must be independent of gauge. That says the wave function must be transformed under gauge transformation in this way to make the gauge dependence exactly cancel. That's it.